Time, for most people, feels like a constant, always ticking forward, unchanging in its flow. We experience it through the rhythm of our lives, sunrises and sunsets, clocks ticking on the wall, and the steady aging of living things. But what if this experience of time isn't universal? What if time could actually stretch or shrink depending on how fast you're moving? This strange and counterintuitive idea lies at the heart of a concept in physics known as time dilation. First proposed by Albert Einstein in his theory of special relativity in 1905, time dilation suggests that the faster you travel, especially close to the speed of light, the slower time moves for you relative to someone who remains stationary. This means that time isn't a fixed, absolute background to all events in the universe. Instead, it can warp and bend based on motion and gravity. Einstein's revolutionary idea challenged the Newtonian concept of absolute time, the idea that time flows at the same rate for everyone, everywhere. Instead, he introduced the idea that time is relative, tied to the speed at which an observer is moving. This was more than just a philosophical shift. It had real, measurable consequences. In Einstein's framework, space and time are woven together into a single four-dimensional fabric called spacetime, and the geometry of this spacetime can change depending on speed and mass. When an object moves very quickly, especially at speeds approaching the speed of light, time slows down for that object relative to observers at rest. This doesn't mean the traveler feels anything strange. For them, time feels normal. But when they return to compare clocks with those who stayed behind, a difference appears. This isn't just theoretical physics. It's been confirmed by experiments. Scientists have flown atomic clocks on airplanes and compared them to identical clocks on the ground. The ones in the air, moving faster, showed slightly less time had passed. In extreme conditions like those experienced by GPS satellites orbiting Earth, engineers must even correct for time dilation to keep navigation accurate. Thus, Einstein's radical notion is not just a curiosity of theory, but an everyday part of modern technology. Understanding how speed bends time requires a bit of mathematics, specifically, the famous Lorentz factor, which arises from the equations of special relativity. When an object moves at a velocity v, the time it experiences, often called proper time, is related to the time experienced by a stationary observer through the following formula. In this equation is the time experienced by the moving object, t is the time measured by the stationary observer, v is the velocity of the moving object, and is the speed of light in a vacuum, c approximately 299,792,458 meters per second. The expression is known as the Lorentz factor, and as v approaches, this factor approaches zero, causing time to stretch significantly. For example, if a spaceship were to travel at 90% of the speed of light, the Lorentz factor would be approximately 2.29, meaning that time on the spaceship would pass less than half as fast as on Earth. If someone on the spaceship experienced just 1 year, someone back on Earth would have aged more than 2 years. At even higher speeds, say 99.99% of the speed of light, the time dilation effect becomes extreme. A traveler might experience only a few months of time while decades pass for observers on Earth. This has profound implications for space travel. If we could ever travel near light speed, humans might visit distant stars within a human lifetime. But when they return, hundreds or even thousands of years might have passed on Earth. Thus, time dilation allows for a kind of one-way time travel into the future. Though the traveler remains young, the rest of the universe continues to age at its normal pace. This potential future is not science fiction. It's grounded firmly in the laws of physics as we currently understand them. Moreover, this effect isn't limited to objects in space. Even particles in laboratory settings experience time dilation. For example, muons, subatomic particles created in the upper atmosphere, decay quickly, in a fraction of a second. But those moving at near light speed live much longer from the perspective of Earth observers, because time for them is slowed down by their velocity. These kinds of real-world confirmations show that the equations of special relativity are not just mathematical games, but accurate descriptions of how the universe behaves. While special relativity explains time dilation due to speed, Einstein didn't stop there. In 1915, he developed his general theory of relativity, which extended the concept to include gravity. According to general relativity, massive objects like stars, planets, and black holes warp the fabric of spacetime around them. This warping not only bends the path of light and affects how objects move, it also changes how time flows. The stronger the gravitational field, the slower time passes near that object compared to regions with weaker gravity. This is known as gravitational time dilation. This effect, though subtle on Earth, has been confirmed through incredibly precise experiments. For instance, in 1976, NASA launched a hydrogen maser clock aboard a rocket to an altitude of about 10,000 kilometers. The clock experienced less gravity and ticked slightly faster than an identical clock on Earth, precisely matching Einstein's predictions. Today, we account for gravitational time dilation in GPS satellites. These satellites orbit the Earth where gravity is weaker, and if we didn't correct their onboard clocks, GPS positioning would drift by kilometers each day. Gravitational time dilation becomes even more dramatic near extremely massive objects like black holes. Near the event horizon, the boundary beyond which nothing can escape, time slows down to such an extent that, from an outside observer's point of view, it nearly stops. This concept was famously visualized in the 2014 film Interstellar, where astronauts visiting a planet near a massive black hole experienced just hours, while years passed for people elsewhere. While Hollywood took some creative liberties, the basic science is grounded in real physics. The closer you are to a strong gravitational source, the more time stretches. These effects highlight an important truth: time is not a universal constant. It is shaped and bent by both motion and mass. As such, time is deeply connected to the very structure of the universe. Our intuitive sense of a single, shared no is an illusion. Instead, what is now for one person might be in the future or past for someone else, depending on their motion or location in a gravitational field. This profound insight continues to reshape our understanding of the cosmos. Time dilation might sound like science fiction, but it has been proven time and again through experiments and plays an essential role in modern technology. Perhaps the most well-known and accessible example is the Global Positioning System (GPS). GPS satellites orbit Earth at high speeds and at altitudes where Earth's gravity is slightly weaker. Both effects, their speed and their position, in a different gravitational potential, cause their onboard atomic clocks to tick at a slightly different rate than identical clocks on the ground. Without corrections for these relativistic effects, GPS signals would become inaccurate by several kilometers each day. Another striking example comes from particle physics. In high-energy particle accelerators, particles like muons are created and then travel at speeds close to the speed of light. Under normal conditions, muons decay in about 2.2 microseconds, but when they move at relativistic speeds, their lifespans appear significantly extended from our point of view. This is direct evidence of time dilation in action. Similarly, cosmic rays create muons in the upper atmosphere that should decay before reaching the ground, yet they are detected at the surface because their moving clocks tick more slowly due to their high speeds. In 1971, an experiment known as the Hafele Keating experiment flew 4 atomic clocks around the world on commercial airliners. After comparing them to stationary clocks, the results showed measurable differences consistent with both special and general relativity. Clocks that moved eastward, in the direction of Earth's rotation, experienced more time dilation than those that flew westward, aligning perfectly with Einstein's predictions. Moreover, scientists continue to refine and test relativity using more precise instruments. Recent developments in optical lattice clocks, which are accurate to within 1 second every 15 billion years, have allowed researchers to measure the time difference caused by a vertical height change of just a few centimeters. That means time moves faster at your head than at your feet. A mind-blowing result and a testament to how far experimental physics has come. These experimental confirmations not only validate Einstein's theories but also provide crucial tools for further exploration. As we develop technologies that involve high-speed travel, deep space exploration, or quantum-level measurements, understanding and accounting for time dilation becomes more important. It also opens the door to possibilities like long-duration space missions, where astronauts could return younger than those left behind, a phenomenon once thought to belong only in science fiction. Time dilation challenges our deepest intuitions about reality. The idea that two people can experience different amounts of time based solely on how fast they're moving or where they are in a gravitational field forces us to rethink what we mean by the flow of time. Is time a real thing that flows uniformly, or is it a human-made measure of change in an ever-evolving universe? Einstein showed us that time is not separate from space. Instead, they are part of the same fabric, and that fabric can stretch, bend, and twist. This has profound implications for our understanding of identity, memory, and even the possibility of time travel. If time can slow down or speed up, then perhaps the boundaries between past, present, and future are more fluid than we think. Some interpretations of relativity suggest that all moments in time, past, present, and future, coexist in a block universe, where the passage of time is a matter of perception, not objective flow. In this view, the universe is more like a four-dimensional sculpture, and what we call now is simply the slice we're currently experiencing. As we look to the future, the practical applications of time dilation might become increasingly important. If humans ever build spacecraft capable of near-light speed travel, time dilation would not just be an abstract concept, it would become a lived experience. Astronauts on long journeys might return to Earth having aged just a few years while centuries passed here. This could redefine our notions of generational knowledge, cultural continuity, and even what it means to be human. There's also the possibility that better understanding of time dilation could help us unlock deeper secrets of the universe. Might it be possible to harness time dilation in new ways? Could we develop technologies that manipulate spacetime, perhaps enabling controlled time travel? While such ideas remain speculative, they are not beyond the realm of serious scientific consideration. Already, concepts like wormholes and warp drives, though still hypothetical, are being explored within the framework of general relativity. Ultimately, time dilation reminds us that the universe is far stranger than it seems. It humbles us, forcing us to question assumptions we once held as absolute. It also inspires us, inviting us to explore beyond the boundaries of our everyday experiences and to imagine what might lie just beyond the reach of our current understanding. In a very real sense, time dilation bends not only time, but also our very perception of reality.